Metals and nonmetals. Metals: iron, copper, aluminium, magnesium, sodium, lead, zinc. These are the few examples of metals. Physical properties of metals. 1. Metallic luster. Metals will have a shiny surface when they are in pure state. This property is called metallic luster. Hardness of metals. All metals except mercury are solids. Metals like iron, copper, and aluminium are hard, whereas alkali metals like sodium, potassium, and lithium are soft and can be cut into bits using a knife. Malleability. Some metals can be beaten into thin sheets. This property is called malleability. Gold and silver are most malleable metals. Ductility. Certain metals can be drawn into thin wires. This property is called ductility. Gold is the most ductile metal. 1 gram of gold can be drawn into 2 kilometers lengthy wire. Conduction of heat. Metals like copper and silver are good conductors of heat, whereas lead and mercury are bad conductors of heat. Conduction of electricity. Silver, copper, and gold are good conductors of electricity. High melting point. Metals have high melting points. Tungsten is the metal with highest melting point, whereas gallium and cesium are the metals with lowest melting points. Sonority. Certain metals produce a ringing sound when hit against a hard surface. This property is called as sonority. Such metals are called sonorous. Nonmetals. Carbon, sulfur, iodine, oxygen, hydrogen are some examples of nonmetals. Physical properties of nonmetals. Nonmetals may be solids, liquids, or gases at room temperature. Most of the nonmetals are either solids or gases. Bromine is the only nonmetal that exists in liquid form. Nonmetals are brittle, hard, but easy to break or crack. Most of the nonmetals are bad conductors of heat and electricity except graphite. Graphite is an allotrope of carbon. It is a good conductor of electricity. Nonmetals are non-lustrous. That means they are dull in their appearance. But here there is an exception to iodine. Iodine is a nonmetal, but it is lustrous. Reactivity with water. Most nonmetals produce acidic oxides when dissolved in water. Chemical properties of metals. Metals burning in air. When metals are burnt in air, they produce metal oxide. For example, when copper is burnt in air, it produces copper oxide. 2Cu plus O2 gives rise to 2CuO. Reaction of metals with oxygen. Metals like sodium and potassium are highly reactive with oxygen. They may catch fire by just exposing them to oxygen. That is the reason why they are stirred by immersing in kerosene. Metals such as magnesium, aluminium, zinc, and lead naturally form a thin oxide layer on their surfaces when exposed to air. This oxide layer acts as a protective barrier that prevents the underlying metal from further oxidation and corrosion. We can make this protective layer even thicker to improve its resistance to corrosion. Anodizing is a process to make a thicker protective layer on metals like aluminium. Anodizing process. A clean piece of aluminium is taken for the process. The aluminium piece is placed in a solution of dilute sulfuric acid and connected to an electrical circuit as the anode, means positive electrode. When electricity flows through the solution, oxygen gas is produced at the surface of the aluminium. This oxygen reacts with the aluminium to form a thicker oxide layer. This thicker oxide layer can be dyed in various colors to give the aluminium an attractive finish. Iron does not burn when heated, but iron filings burn vigorously when sprinkled into a flame. Silver and gold do not react with oxygen even at high temperatures. So, metal plus oxygen gives rise to metal oxide. Amphoteric oxides. Generally, metal oxides are basic in nature, but some metal oxides like aluminium oxide and zinc oxide show acidic as well as basic behavior. Such metal oxides are called amphoteric oxides. Solubility of metal oxides. Most of the metal oxides are insoluble in water, but sodium oxide and potassium oxide dissolve in water and produce alkalis. Na2O plus H2O gives rise to 2NaOH. K2O plus H2O gives rise to 2KOH. Reaction of metals with water. Metals react with water and produces metal oxide hydrogen. This metal oxide further dissolves in water and produces metal hydroxide. Metal plus water gives rise to metal oxide plus hydrogen. Metal oxide plus water gives rise to metal hydroxide. Example, 2K plus 2H2O gives rise to 2KOH plus H2 plus heat energy. Reaction of metals with acids. Metals react with acids to give a salt and hydrogen gas. For example, magnesium plus hydrochloric acid gives rise to magnesium chloride plus hydrogen gas. Mg plus 2HCl gives rise to MgCl2 plus H2. So, a metal plus dilute acid gives rise to salt plus hydrogen. Reaction of metals with solution of other metal salts. Highly reactive metals will displace less reactive metals from their compounds in a solution. For example, zinc reacts with copper sulfate solution and forms zinc sulfate and copper metal. Here zinc is more reactive than copper as it is higher in the reactivity series. Reaction between metals and nonmetals. When metals react with nonmetals, electrons are transferred from the metal atoms to the nonmetal atoms forming ions. The resulting compound is called an ionic compound. Properties of ionic compounds. Physical nature. Ionic compounds typically exist as crystalline solids. They are hard since the anions and cations in them are held together by strong electrostatic forces. Melting and boiling points. Ionic compounds have high melting and boiling points. For example, the melting point of sodium chloride is 801 degrees Celsius and the boiling point is 1465 degrees Celsius. Solubility. Ionic compounds are soluble in water and insoluble in solvents such as kerosene, petrol, etc. For example, sodium chloride dissolves in water but not in petrol and kerosene. Increasing the concentration of valuable minerals or metals while reducing the content of impurities. This is done by various physical and chemical methods Metals like gold and silver are low in the activity series and are very unreactive. The oxides of these metals can be reduced to metals by heating alone. Extracting metals middle in the activity series. Metals like zinc and lead are in the middle of the reactivity series. They are usually present as sulfides or carbonates in nature. Extracting metals middle in the activity series. Metals like iron, zinc, lead and copper are found in the middle of the reactivity series. These metals are usually found in nature as sulfides, means combined with sulfur, or carbonates, means combined with carbon and oxygen. Before extracting the metal, the sulfide or carbonate ores need to be converted into their oxides, because it is easier to extract metals from their oxides rather than from sulfides or carbonates. Sulfides and carbonates are converted into oxides by roasting and calcination methods. First, let us see roasting. Roasting is the process of heating a sulfide ore in the presence of excess air or oxygen. The main purpose of roasting is to convert these sulfide ores into oxides. For example, roasting of zinc sulfide. The roasting process can be represented as 2ZnS plus 3O2 by heating 2ZnO plus 2SO2. In this reaction, zinc sulfide is heated in the presence of excess oxygen and it gets converted into zinc oxide while releasing sulfur dioxide as a byproduct. Next, calcination. Calcination is the process of heating a carbonate ore in the presence of limited air or in the absence of air. The primary purpose of calcination is to convert the carbonate ores into oxides. For example, calcination of zinc carbonate. The calcination process can be represented as ZnCO2 gives rise to ZnO plus CO2 in presence of heat. Here zinc carbonate is heated and it decomposes into zinc oxide and carbon dioxide gas is released. Reduction of metal oxides. Now let us see reduction of metal oxides. Once the metal oxides are obtained from their respective ores through roasting or calcination, the next step is to reduce these oxides to obtain the pure metal. This reduction is typically carried out using a reducing agent such as carbon in the form of coke or charcoal. It removes the oxygen from the metal oxide. During this process, the metal oxide loses oxygen, which is taken up by the carbon, and the metal is left behind. For example, when zinc oxide is heated with carbon, a chemical reaction occurs in which carbon acts as the reducing agent. The reaction can be represented as zinc oxide plus carbon gives rise to zinc plus carbon monoxide. When zinc oxide is heated with carbon, the carbon combines with the oxygen from zinc oxide to form carbon monoxide. The zinc oxide loses its oxygen, that means it is reduced and is converted into pure zinc metal. This reduction of metal oxides can be done not only by using carbon, but also through displacement reactions. A more reactive metal is used to displace a less reactive metal from its compound. When manganese dioxide is heated with aluminium powder, a displacement reaction occurs. Aluminium, being a highly reactive metal, it acts as a reducing agent. It displaces manganese from manganese dioxide, reducing it to metallic manganese while oxidizing itself to aluminium oxide. The reaction between manganese dioxide and aluminium can be represented as 3MnO2 plus 4Al gives rise to 3Mn plus 2Al2O3 plus heat. Aluminium being more reactive than manganese, it removes the oxygen from the manganese dioxide, reducing it to manganese metal. This type of reaction is also called as a thermite reaction because it is highly exothermic. That means lot of heat is released in this reaction. The heat generated from the reaction is often sufficient to melt the metal that is produced. That means whatever the final metal formed in this reaction, it gets molten because of the heat generated in this reaction. Applications of thermite reaction. Welding railway tracks. The intense heat from the thermite reaction is used to weld railway tracks by producing molten iron, which fills the gaps and solidifies to form a strong bond. The thermite reaction that is used in railway track welding is as follows. Fe2O3 plus 2Al gives rise to 2Fe plus Al2O3 plus heat. Iron oxide plus aluminium gives rise to iron plus aluminium oxide. Another application of thermite reaction is repairing cracked machine parts. The molten metal from the reaction can be used to fill cracks in the machine parts. Extracting metals top of the activity series. Potassium, calcium, sodium, these metals are high up in the reactivity series, which are very reactive. These metals are obtained by electrolytic reduction. For example, sodium, magnesium, and calcium are obtained by the electrolysis of their molten chlorides. Refining of metals. The metals produced by various reduction processes described above are not very pure. They contain impurities which must be removed to obtain pure metals. The most widely used method for refining impure metals is electrolytic refining. Corrosion. Corrosion is the gradual deterioration of a material due to chemical reactions with its environment. Mostly it happens by oxidation. Silver articles become black by reacting with sulfur in the air to form a coating of silver sulfide. Copper reacts with moist carbon dioxide in the air and gains a green coat of copper carbonate. Iron metal reacts with oxygen in the air in the presence of water and forms iron oxide. This process is called rusting. Prevention of corrosion. To prevent rusting, we use different methods. Painting, covering the metal with paint to keep air and moisture away. Oiling, applying oil to create a protective layer. Galvanizing, coating iron with a layer of zinc. Even if the zinc coating breaks, it still protects the iron underneath. Chrome plating, adding a thin layer of chrome to make the metal shiny and rust resistant. Using alloys, mixing metals with other substances to improve their properties. For example, iron and carbon. Adding carbon to iron makes it stronger. Nickel and chromium. Adding these to steel makes it resistant to rust, creating stainless steel. So these methods show us how combining different materials can change and improve the properties of metals.